All right, so back to part two. Again, quick review of our theorem here. That says if we can establish a power series has a radius of convergent r is greater than 0, then the function f can be defined as we saw, and we can differentiate it. And we talked about, again, make sure you change your n to 1 once you lose that first term, c sub 0, that's going to change to a 0, and we can integrate it. All right. So example 4, for f of x, find the interval of convergency for f of x and f prime of x. So remember, when you take the derivative or you integrate, your endpoints may change. So again, we're using the ratio test where now we have to check the endpoints, whereas before we didn't because we were comparing it to a geometric series where we could not be equal to 1 at all. All right, so for our limit test, we're going to start with our a sub n plus 1. So notice that every n has a plus 1 to it, so that's going to change them all to plus 2's. And then we divide by our original sequence function, or as we've said before, multiply by its reciprocal. So we can do some simplifying here. We can break this x minus 1 to the n plus 2 down to x minus 1 to the n plus 1 times x minus 1, and then cancel out the x minus 1 to the n plus 1 powers. Next, we can cancel our negative 1 to the n plus 1 and the negative 1 to the n plus 2. There'd be one negative left over, so we'll leave that there. And so here's what we have it simplified to. The limit as n approaches the absolute value. Again, remember we said group the n's together as one factor, group your scalar factors and your x expression as another. Well, the negative 1 is going to disappear because the absolute value of negative 1 is 1, so we don't need that anymore. Then let's take the limit as n approaches infinity here. Well, the powers are the same. Again, you can use that quick horizontal asymptote rule in saying that your leading coefficient is going to be your limit, so that would be a 1. So our answer is the absolute value of x minus 1. So we converge as long as we're less than 1 by the ratio test. And we'll create your compound inequality. Negative 1 is less than x minus 1 is less than 1. To remove the absolute value bars, add the 1 to both sides. And so our interval of convergence so far is at 0 to 2. But now again, we have to test our endpoints. All right, we have our r, our radius of convergence is 1. We have our beginning interval of convergence. We test the 0. So we're going to put 0 in for x. So going back to the original series, your summation setup, we put 0 here, so that's going to give us 2 negative 1's to the n plus 1. Well, multiply like base as you add everything together. Well, this is always going to be an even, so this is going to be a positive 1. And so 1 over n plus 1, we can see already what's going to happen. This is going to be a p-series. It's a harmonic series, if you will. We know that diverges. And with your limit test, we would check the limit of 1 over n plus 1 times, or divided by 1 over n, what we compared it to. In this case, we're multiplying by its reciprocal, n over 1, and that too has a limit of 1, which is greater than 0, and the limit comparison test verifies that this diverges. So therefore, excuse me, we're not going to change the 0. It's going to stay as an open interval, no equal to line. We test x equals 2. We put 2 up in for x. 2 minus 1 will be 1. So 1 to the n plus 1 power is just going to be 1. So we're just going to be left with a negative 1. So here we use the alternating series test. Drop the negative 1, if you will. Replace it with a 1. We see that the limit goes to 0. That satisfied test number 1. Then we just got to make sure that this is decreasing. So 1 over n plus 2 is less than or equal to 1 over n plus 1. And if you cross multiply, or you can see that this denominator is bigger, which means it's going to be smaller than this denominator over here, or this fraction. So that's true, and this converges. So we're going to have to change the parentheses on the 2 to a bracket. So there is our interval for convergence for our f of x. All right, so now we've determined Our interval, now let's look at f prime. F prime of x will have the exact same radius as the definition said. That's not going to change, but you got to check the endpoints. So what we're going to have to do is we have to go find the derivative of this. So -1 to the n plus 1 is not going to change. That's a constant. The n plus 1 is multiplied to the front. We reduce the power by 1, so now it's x minus 1 to the n power. And then we take the derivative of the inside because it's technically a chain rule, and the derivative of x is 1. And I put that there just to remind you to make sure you do that. So now the n plus 1 and the n plus 1 are going to cancel. And again, we don't need that 1. That's not going to make any change. So here's my series. Let's test it now when x is equal to 0. So we'll put a 0 here, which means we're going to have -1 to the n plus 1 times -1 to the n, where if you add your exponents, because you're multiplying like bases, you're going to get 2n plus 1, which guarantees this to be odd all the time. So we're going to have -1 plus -1 plus -1. Well, that's going to diverge. All right, that sum just keeps getting smaller and smaller. -1, -2, -3, -4, -5. It's just going to keep on getting bigger in a negative direction. We test the 2. 2 minus 1 is 1. So again, 1 to the n power is not going to make a change to anything. So it's -1 to the n power. So this is going to oscillate from being a positive to a -1 back and forth. So that diverges. So in this case here, your endpoints are going to have open intervals for the derivative of our power series, of our f of x, if you will. All right, so if we want to find a power series for 1 over 1 minus x to the second power and its radius of convergence, kind of the same thing here. We know that 1 over 1 minus x is equal to this summation. We just need to get that squared. Well, to get it squared is we have to take the derivative of that 1 over 1 minus x. So if we take the derivative of that, remember, think about moving this up to the top with a negative exponent. Move the -1 out front, subtract 1 from the power, -1, and chain rule, take the derivative of the inside, that's -1. So -1 times -1 is a positive 1. So the derivative of our power series here that we've defined in the past is equal to this 1 over 1 minus x squared. So we can take the derivative of both sides of this equation and find our power series for 1 over 1 minus x squared. So let's go ahead and take the derivative of that. We already know that the derivative of this is going to be the 1 over 1 minus x to the second power. Take the derivative of our summation. All right, now remember what's going to happen when we take the derivative. What's going to happen to our 0 is it's going to change to a 1. All right, so that means our n comes down in front. We reduce our power by 1, and there's our summation, but we're now starting at a 1. And again, your radius of convergence is still 1. Again, remember why that happens? That's that constant that disappeared. So we no longer start at 0, we start at 1 to find our first term of our derivative. Okay, find a power series for x over 1 plus 4x all to the second power and the radius of convergence. So let's make this look like our 1 minus r. So we're going to change the plus to a minus or -4x. So a is 1, r is -4x. We put that into our summation formula. So our -4x, that absolute value is less than 1. So the absolute value of x is going to be less than 1/4. So that's my radius. Once you get that absolute value of x by itself, that's going to be your value here. All right, so 1 over 1 plus 4x is equal to the summation of n equals 0 to infinity of -4 to the n power times x to the n power. So I'm just breaking this down. Now remember, our original had an x up in the numerator. We'll take care of that once we get there. We're just trying to set up the 1 over 1 plus 4x to get it to be 1 over 1 plus 4x, the binomial squared, and then we'll figure out how to get the x in there. So just like the previous problem, we're going to take the derivative of both sides. Well, we know over here we're going to get negative 4 over 1 plus 4x squared. Remember, this is 1 plus 4x all to the negative 1 power, so the negative 1 comes out in front. The derivative of the inside is going to be 4, so the negative 1 and the 4 become the negative 4 up in the numerator. Over here, the negative 4 to the n power, no change, that's a coefficient. Bring the n down, multiply it to that coefficient, if you will, times x to the n minus 1 power. And again, don't forget to change your n equals 0 to n equals 1. Now, we're almost there, except we want an x on the top, not a negative 4. That's what we really want on the left side. So to get that, we need to cancel out the negative 4, and we need to multiply by an x to the top. So we're going to multiply both sides by x over a negative 4. So the negative 4's will cancel, and x is now on the top on the left side. Over here, the negative 4, we'll divide it from one of these negative 4s, so that means we're just subtracting 1 from our n. And here's our power series. Now, if we wanted to, we could clean this up a little bit, take the negative out of the 4. We could make some adjustments. Again, these are both correct answers. They're all good. You can even rewrite it with n equals 0. You just have to add a 1 to every place you see an n, because you're backing it up 1, so you have to add 1 to all your n's. So the n minus 1 on the negative 1 becomes n, the n minus 1 on the 4 becomes n, the n out in front becomes n plus 1, and the n on the power becomes n plus 1. So these are both acceptable answers, and even this answer is good too. Okay, find a power series for the natural log of 1 plus x and its radius of convergence. Well, we know that the derivative, come on, stupid mouse. All right, so we know that the derivative of the natural log of 1 plus x is 1 over 1 plus x. That's what we want, except we would prefer to get it as 1 minus x, so we have that. So we can make that change. So what we're going to do is, once you've taken the derivative of both sides, then we're going to integrate both sides. So if I integrate the left side, I'm back to the natural log of 1 plus x. So if we integrate our fraction over here, 1 over 1, now we change it to minus and negative x, so we get into that 1 over 1 minus r form for our power series. We can take care of the integration. We can also find our radius of convergence, take our negative x into the absolute value bars, set it less than 1, so r is going to be your 1. And again, the negative is going to disappear, but you still keep the absolute value bars around your x. And we know we can swap this out for a, which is 1, times r, negative x to the n power. So this all gets swapped out to this summation. So we can integrate this now first on the inside. So this is going to become n plus 1 all divided by n plus 1 on the bottom, plus your c. Now, do a little simplifying here. The negative 1, we can change that to the minus 1 power if we change this to a 1. We can change the n plus 1s and the n plus 1s to just n by subtracting 1. So remember, if you're at 1 and you want to go down to 0, you add 1 to the n's. If you want to go 0 up to 1, you subtract 1 from all your n's. These are both acceptable answers here. Now, the one thing we also want to do is we want to find the value of c. We want to know what that constant is. So to find c, let x equal 0. So there's a 0 there. So that's the natural log of 1, because if you put 0 in for x here, this all zeroes out, and the only thing you have is a summation of 0, which is 0 plus c, equal to the natural log of 1 plus 0. So the natural log of 1 is 0, so our constant is 0, so we can drop the c's. So again, the natural log of 1 plus x could be equal to the summation that starts at the 1, or you can have the 1 with the 0. They're both good. But again, traditionally, we like to start with the 1 for our 1 minus 1 over r for our geometric series. Okay, number 8, find the power series for f of x equals the inverse tangent of x. We know that the derivative of the inverse tangent of x is 1 over 1 plus x squared, so that's what we're going to need to use. Again, we're going to integrate both sides to get rid of the derivative on our inverse tangent. We're going to change our plus to minus a negative x squared. So again, just like we saw before, negative x squared becomes x squared less than 1. It's going to be the square root of both sides. It's still going to have a 1 for your radius of conversions. So now we change our 1 over 1 minus the negative x squared. A is 1. R is the negative x squared raised to the n power, with n equals 0 to infinity. And now we can integrate this. So again, we're going to break apart the negative 1 raised to the n power, the x to the 2n power. So if I integrate my x with respect to x, I'm going to add 1 to the power and divide by 2n plus 1 on the bottom. So again, we can take our c value, figure out what that's going to be. So if I put 0 in for all my x's, everything zeroes out here. I put 0 in for the inverse tangent. That is also 0. So c is equal to 0. We can drop it off. And again, if you wanted to, we can change this to a 1. All right, so if I increase this to a 1, then you just have to adjust all your n values. So this would be an n minus 1. This would just be x to the 2n all over 2n. Again, they're both acceptable. Use a power series to approximate the definite integral to 6 decimal places. So we're going to have to recall that alternating series sum theorem that we talked about. So again, what we're going to do here is we're going to take our x squared over 1 plus x to the 4th. We're going to take off the x squared, factor it out. 1 over 1 minus a negative x to the 4th. So a is 1, r is a negative x to the 4th. And we keep the x squared multiply out front of our summation. Then what we can do is, after you set up the basic form of your power series, we can bring the x squared back. So we're going to have the negative 1 factored out as just negative 1 to the n power. Then you have x to the 4n power being multiplied by x to the n. That gives us x to the 4n plus 2, so we can move this all back inside of our summation symbol. So now we're going to integrate it with from 0 to 0.3. So again, we integrate our summation. So that means we'll take and integrate the inside. So the summation of negative 1 to the n power, this becomes x to the 4n plus 3. We add 1. And then divide by 4n plus 3, and then we're going to evaluate it from 0 up to 0.3. Well, if we put 0 in for x, again, this is all going to cancel out, so we're just going to minus a 0. So we put in our 0.3 for x, and then we're going to find this summation of negative 1 to the n power of 0.3 to the 4n plus 3 over 4n plus 3. So to find this sum to 6 decimal places, we're probably going to have to write this all out like we did before, the sum, s equals 0.3 to the 3rd power. Again, n starts at 0. So 0, that's a positive first term. So now we know that they're going to all alternate from there. And then 4 times 0 gives me 3 on the bottom. Minus, I put in the 1. So 4 plus 3 is 7. So 0.3 to the 7 over 7. Plus 0.3 to the 11. I just put in the 2's, then I put in a 3. And what I did is I went to my calculator to start looking for 6 decimal places that are zeros. So I typed in without the -1 in there because I don't need that part. So I looked in my table, 0.009, not small enough. Here I have e to the -5, so that would be 4 zeros after the decimal place, not small enough, need to go to 6. And here it's e to the -7, which means there would be 6 zeros in front of that 1, 6. So that third term, when I looked it up at the bottom of the screen, was 0.000000161. And then I think there was another 0, and I just said, we'll just stop there. So remember our alternating series summation approximation. S sub n minus b sub n plus 1. Remember the neglected term? That's going to be this one, because now this difference is small enough that it's not going to change out to 6 decimal places. Is less than or equal to s, less than or equal to s sub n plus b sub n plus 1. Well, if this was the third term, then n plus 1 to be 3 means n would have to be 2. So s sub 2. So we're going to add these two terms together, and then we're going to subtract that decimal there in red. So adding the first two fractions together in your calculator gives you 0.009031249. Subtract the third term, add the third term, crunch those decimals, and if you notice, out to 6 decimal places here, 1, 2, 3, 4, 5, 6, we end up with a 031. 1, 2, 3, 4, 5, 6, they're exactly the same. So out to 6 decimal places, if we drop, say, let's round to 6 decimal places, they're the same values. So we can now say, okay, this integral is approximately going to equal 0.009031 to 6 decimal places, and that's what we were asked to do. If you tried to integrate this, there's no u substitution you can use because your powers aren't lined up properly on your x's. Oops. I tell you, this mouse is getting too sensitive for me. So here is an integral that is very difficult to integrate the way we've done in the past, but by changing it into a power series, then integrating, we can use our alternating series sum to find those values. So make sure you know this example here because that's a good one for the test. And that ends part 2.